Okay, today we are diving into one of the biggest, most important unsolved problems in all of computer science and really all of mathematics. It's a question that's so profound it secretly touches almost everything you do, from how your packages get delivered to the very security of the entire internet. And, if you solve it, you get a little more than just bragging rights.
Yeah, a lot more. The Clay Mathematics Institute has this list, the 7 Millennium Prize Problems, and P versus NP is right there on it. If you can solve it and prove you solved it, you not only write your name into history, but you also walk away $1 million richer.
And you want to know who gets a lot of these attempted solutions? The guy who basically helped kick off the entire field, University of Toronto's Stephen Cook. Can you imagine that? Defining a problem so famous that for the rest of your life, your inbox is just this constant stream of people absolutely convinced they've cracked the code.
So what is this thing? What is this ghost in the machine that haunts the world of computer science? What is the P versus NP problem actually asking? Well, it boils down to something that sounds surprisingly simple.
That's it. That is the million-dollar question right there. It's a question about the very nature of difficulty. Think about it. If you can easily tell a correct answer when you see one, does that automatically mean there's an easy way to find that answer in the first place?
To really wrap our heads around this, we got to break down the alphabet soup here. P, NP, and this other crucial category, NP complete. It all comes down to the difference between solving a problem from scratch versus just checking if an answer is right.
Okay, so this distinction is everything. Problems in P, that P stands for polynomial time, are the ones computers can solve efficiently. Think about sorting a huge list of names. It takes time, but the time it takes grows in a predictable, manageable way. It doesn't spiral out of control. Now, problems in NP are different. They're the ones where a solution is easy to check. Like, if I hand you a finished Sudoku puzzle, you can very quickly verify that, yep, all the numbers are in the right places. But finding that solution from a blank grid, that can be a total nightmare. So the P versus NP question is really asking, are these two groups of problems actually the same group?
This right here is the poster child for NP problems. If you have, say, 4 or 5 cities, you can sketch out every possible route, no problem. But with every single city you add, the number of possible routes just explodes. It gets out of hand, and I mean fast.
And this just perfectly illustrates the mind-boggling scale we're talking about. To figure out the ultimate UK pub crawl, researchers had to use all sorts of clever optimization tricks, because trying to brute force it, forget about it. For just 50 cities, not 50,000, just 50, a computer would need longer than the age of the universe to check every single route. That's the kind of insane difficulty we're up against.
Now this is where the real genius of Stephen Cook's 1971 paper comes in. He identified this special class of problems within NP, the NP-complete ones. These are the bosses, the hardest of the hard. And here's the crazy part. They're all connected. The Traveling Salesman, Sudoku, complex scheduling, protein folding, thousands of seemingly unrelated problems. If you find a fast, efficient solution for just one of them, you've automatically found a solution for all of them. You've proven P equals NP.
So let's just imagine for a second that someone does it. They prove P equals NP. What would that world actually look like? Well, the consequences would be absolutely staggering, in ways that are both incredible and, frankly, terrifying. A computer scientist named Russell Impagliazzo actually gave this hypothetical world a name. He called it Algorithmica. It's a world where that spark of creativity, that genius leap to find a solution, is no harder than the boring mechanical task of just checking it.
In Algorithmica, we could solve some of the biggest problems facing humanity. We could design life-saving drugs by perfectly modeling how proteins fold. We could create flawless shipping routes, eliminating waste. We could even have AI that could generate beautiful new art or prove new mathematical theorems. But the flip side is total, absolute chaos. The entire security of our digital world, your bank account, your private messages, government secrets, everything is built on the assumption that some problems are just too hard to solve quickly. If P equals NP, that assumption goes up in smoke. Every form of modern encryption would be shattered overnight.
So, given that the internet hasn't collapsed yet, it's a pretty safe bet we don't live in Algorithmica. Most scientists are pretty convinced that P does not equal NP, but we might be moving towards really fascinating middle ground.
And this is why it matters so much. Our entire digital life is balanced on the belief that P and NP are different. As computer scientist Tony Patassi explains, if we could actually prove P is not equal to NP, it would be a massive step toward formally proving that our security systems are actually secure.
But here's where it gets interesting. A researcher named Lance Fortnow suggests we're not heading for Algorithmica, but for a world he calls Optiland. It's a place where we kind of get the best of both worlds, many of the amazing benefits of P equals NP, but without the whole breaking the internet downside.
Think about it. We're using things like machine learning and just sheer computing power to find these amazing, good enough solutions to hard problems. DeepMind's AlphaFold is making incredible progress on protein folding. We're getting better at weather prediction. We're getting a taste of Algorithmica's upside, while our passwords and bank accounts stay safe because we're not quite solving those problems in the perfect, general way that would break everything.
You know, this problem isn't just some abstract idea on a chalkboard. It's a living, breathing quest. It has a rich history and a really vibrant and sometimes brutally honest online community of people who are still trying to claim that $1 million prize. The first whispers of this idea actually appeared way back in 1956 in a letter from the famous logician Kurt Gödel. But the field really blew up in 1971 with Stephen Cook's paper. Then, just a year later, Richard Karp showed that 21 really famous problems were all NP complete. That proved this wasn't some niche little corner of math. It was a concept right at the very heart of computation itself. These days, the hunt for a proof often plays out in public, on forums like the Computational Complexity blog. And let me tell you, when someone posts a new claim that they've solved it, the peer review is swift, it is direct, and it is often absolutely savage. Here's a perfect example. You get a researcher, Jay Connell, who posts this comment. And he's not just throwing out an idea. He's got 12 papers, a machine-checked proof, a huge body of work. He's confidently saying, hey, look at the substance here, because I think I've actually done it. And then the hammer drops. Another expert, Jean Abu Samra, actually goes into the code and finds that the core theorem basically just says, theorem, P is not equal to NP is true. The proof? Oh, it's trivial. And then he just signs off with, allow me to laugh. That is the intense, high-stakes world these folks are playing in. And that's why, after decades of incredibly hard work and countless attempts, some, more serious than others, the problem is still wide open. And that $1 million, it is still sitting safely in the bank. But here's the real takeaway, and maybe the most beautiful part of this whole story. As Lance Fortnow puts it, maybe solving the problem was never the only point. For half a century, the quest to solve P versus NP has forced us to invent whole new fields of mathematics, to develop incredibly powerful algorithms, and to just push the boundaries of what we thought was possible. The problem itself has been this incredible engine for human innovation.
Which leaves us with this last thought to chew on. Is the existence of hard problems a wall that just fundamentally limits what we can do? Or is it a permanent challenge? An opportunity that will forever inspire new ways of thinking, new technologies, and new solutions that we can't even begin to imagine yet. The answer to that, just like the solution to P versus NP itself, is still out there, waiting to be found.